last class we had our first introduction to planning systems. Today's class would be the second lecture on planning. The instructional objectives of today's lectures are the following. We will look at into little more detail into forward search as used for planning problems, forward search or progression. Then we will look at backward search or regression. We will also look at the planning algorithms used in the strip system, and then finally we will start with partial order planning, the framework, and we will explain the basic partial order planning algorithm. So, let us get back to a quick introduction of the planning problem. So, as we have noted earlier, we have an agent which works in an environment. The agent has goals, the agent takes actions, and the actions affect the environment. The agent receives percepts through its sensors from the environment. The objective of the environment is to plan the next action or the next sequence of actions so that it can achieve its goals. So, this is the basic idea of a planning system. Now, before we get into today's lecture, I would like to briefly discuss the questions that we posed in the last lecture. The first question was, explain how planning systems differ from classical search problems. You see, planning is also one type of search. What sets planning apart from a general search problem is that in the case of planning, we can decompose the goal. We do not look at the goal as a whole. So, it is not just that we look to see whether a state satisfies the goal fully or not. Usually, as we have noted, a goal is described as a conjunction of different conditions, different propositions or conjunction of different literals. And so, these can be looked upon as individual sub goals. So, instead of looking at the goal as a whole, it may be more useful if we look at the goal as a conjunction of sub goals, so that we can reason separately about solving each sub goal and then combine the results. This will make the planning problem easier to solve. Secondly, states are also not indivisible entities. States are decomposable. So, states, as we have seen, is described by a conjunction of those propositions that hold or that are true in the state. So, state is described as a set of propositions, and actions are also explained in terms of what propositions must hold at the previous state in order that the action can be executed, that is the preconditions of the action and the effect of the action. So, we concentrate on how the action changes the propositions in the state. So, this is what sets a planning problem apart, or what distinguishes a planning problem from the more general search problems. And the algorithms for planning that we will consider, we will look at these characteristics of the planning problem in order to devise the right algorithms. So, let me briefly discuss now question 2 that we said last week. I wanted you to formulate the Block's world planning problem. Now, for the Block's world planning problem, let us just look at a sample of a Block's world planning problem. Suppose we have the following situation. We have two blocks A and B. B is in top of A, and we have a third block C. So, this is, let us say, this is the initial state of the planning problem. How do we express this initial state? On table A, on B A, clear B, on table C, clear C. So, the initial description of the initial state of the planning problem can be given as conjunction of on table A and on B A and clear B and clear C, and clear C and on table C. So, this is how we can describe a particular initial state in terms of the propositions on table, on and clear. Then we have to specify a description of the goal state. Suppose in the goal state we need to only give a partial specification. For example, I can say that B should be on top of C. Okay. So, this, as you see, is a partial specification of a goal state, and there could be several states which satisfy this condition. For example, this is a state which satisfies the goal condition, B is on top of C. This is another state which satisfies the goal state. There are several states which can satisfy the goal state. Then we represent actions. For example, suppose in the blocks world we can have actions like pick up X, and we specify an action in the strips domain by giving the preconditions of the action and the effects of the action. So, I will not formally write down the entire system because we have already covered it, and we will look at further examples later, but for each action you need to specify the precondition. Can you tell me what would be the preconditions of the pick up X action? So, for the pick up X action, the preconditions could be hand empty and clear X. If X is clear and hand is empty, then the pick up X action can be executed. Now, if pick up X action is executed, what would be the effect? The effect would be not. So, if X is on top of something, suppose X is on top of Y, if on X Y was true in the previous state, on X Y will not be true in the next state. So, that would be deleted, and hand empty will no longer be true after the pick up X action. So, not hand empty. Okay. Similarly, if we look at the action stack X B, what would be the precondition? The precondition has to be that clear B, B has to be clear, and then hand should not be empty and the hand should be holding X. So, if holding X and clear B, then the action stack X B can be performed. After the action stack X B is performed, B will no longer be clear, X will be on B, on X B, and X will be clear. So, let us see. So, for the action pick up X, wait. For the action pick up X, the precondition has to be that clear X, hand empty, and let us say on X Y. What will be the effects? Effects will be not hand empty, not on X Y, and the effect will also be holding X. For the action stack X Y, what would be the preconditions? The precondition has to be that holding X, not a hand empty, clear Y. What will be the effects? The effects will be not holding X, not clear y, hand empty on x y. Okay. Now, let us get on with today's lecture. So, as we have noted that planning problems can be cast as search problems, and in planning we are given an initial state and a goal state, and we have to generate a sequence of actions. And we have also discussed that there are two standard ways in which we can generate the sequence of actions. One is we can do forward state space planning, in which we go from the initial state towards the goal state in order to find the plan, or we can do backward planning. So, let us review the algorithm for forward planner. In a forward planner, initially the agent is in the initial state, and we maintain a search queue, and we put the initial state in the search queue. Then we have a loop. In the loop, we pick a state. So, first step is pick a state from the search queue and examine the state. If it is a goal state, then terminate and return the path from the initial state to this state. Otherwise, if it is not a goal state, we apply all the applicable actions in the state to generate all successes of the state. This is called progressing the state through operator application, and each of the successor states so generated are put in the search queue. So, basically we can do a search, breadth first search in the state space. So, we can go from one state to the states which are distance 1 ahead, then distance 2 ahead, and so on, until we get a state which satisfies the goal description. This is the general breadth first search framework, and this is called forward planning algorithm. Now, this forward planning algorithm is also called progression, and we can write this algorithm in more detail as follows. We are given an initial state I, and we need to go to a goal state which satisfies G. So, the progression of from the current state to the goals given the set of actions available and the path so far. So, if the current state satisfies the goals, then we return the path. Otherwise, we choose actions. Choose from the actions those actions such that preconditions of A is satisfied in the current state. So, actions is the set of all actions. We choose A which are part of actions, and those A for which precondition is satisfied in state. If there is no such A, then we cannot progress that state further. But if such an A exists, or if more than one such A exists, for each such A, we get the next state by applying the action A to state S, to the current state. Then the goals remain the same, the actions remain the same, and path is augmented by adding the current action. So, this is a recursive formulation of the forward planning algorithm. And first call we call progress, initial state, G, actions, and an empty path. Now, forward search, the main problem with forward search is that in certain domains the number of possible actions that you can execute can be very high, and many of these actions may have no bearing to achieving the current goal. So, in such systems, forward search is not an effective mechanism. So, basically in forward search, the branching factor is the number of legal actions. The path length is the number of actions that are required to achieve the goal. In any real world situation, there is just too many applicable actions. There are too many things that you can do. So, if you are considering all possible actions, then the search space can become really huge. So, if you want to use forward planning, you better use some good heuristics to decide which actions you should use. And the other alternative is to not search forward, search in the backward direction. Now, let us see what that means. Before that, let us take a very simple example of a forward search. Suppose initial state, the agent is at Kharagpur, and the goal state is that the agent has to be at Leh, and the actions available are the agent can take a train from Kharagpur to Delhi, take a train from Kharagpur to Chennai, from Kharagpur to Mumbai, Kharagpur to Howrah. So, there are a huge number of possible actions that the agent can do. Agent can take a train to different places, can take a flight to different places, they can walk to different places. The total number of choices is just too huge. So, some of these choices are applicable in the current state, even that can be very large. The agent can take a train from Kharagpur to Delhi, from Kharagpur to Chennai, Kharagpur to Mumbai, Kharagpur to Howrah, and so on. And then for each such state to consider what are the possible actions that it can take. If the agent is not directed by heuristics towards a particular motive, then as you can see, the state space which is explored can be just too huge. Now, one possibility when the branching is very high is to use backward search. What does backward search mean? Backward search means instead of doing a search forward from the initial state, the agent does a search backward from the goal state. So, finds out what he has to achieve and then finds what actions can achieve that goal. If there are a few actions, only a few actions that can achieve the goal, the branching factor can be small in the backward direction compared to the forward direction. But backward search, we have to take care of certain issues. So, you cannot straightforward do backward search from the goal just like we do forward search from the start state. Why? Because for one, the goal does not uniquely specify a state, but it is only a partial description of the state. Remember, in the goal state, we just say these are the conditions that must be true in the goal state, right. So, we do not have the full goal state. Okay. So, but we are given a set of sub goals that we have to achieve, and then we can consider each sub goal separately, and we consider actions that usually achieve one or more of these sub goals. Now, in backward search, we say that an action A is applicable in state S in the backward direction if the effect of A is consistent with S, there is at least one effect of A that is part of S, and the state resulting from applying A in the reverse direction is called the result of regressing S through A. So, we will look at that later. First of all, let us see which are the actions that we will consider from a goal. First of all, you can see the second point is very clear. We must consider an action A whose effect makes at least one condition in the goal valid. Okay. So, you achieve at least one condition of the goal. So, you must select such an action, but you must be careful that the effects of the action is not consistent with what you have at the current goal state. So, if the current goal state says clear C and your effect is not clear C, then that action cannot be executed. So, an action can be executed only if its effects are consistent with the current goal state and it achieves at least one of the propositions in the current goal state. So, we are doing basically goal directed actions which achieve some goal. You see, if the number of actions that can achieve a sub goal is not very high, in such cases backward search can turn out to be much more effective than forward search. Now, let us come to the second question. How do we find the state resulting from applying A in the reverse direction? So, that state is obtained by this. First of all, we collect the preconditions of A. and secondly we add to it the variable value assignment of every state variable which are not in the precondition of A, but in the current state. So, let us just try to see. We have, this is my current state, and we are considering the effect of the action A. Now, in this state, what would be the propositions? Number 1, all the preconditions of A. Number 2, those propositions which are true in S, but they are not in the preconditions of A, we should also add here. So, that would be the partial description of the state which we get by regressing action A in state S. Is this clear? Finally, in backward search, when do we terminate? In forward search, we terminate when the agent gets to the goal. In backward search, the current backward states we terminate when the current backward states partial assignment is consistent with the variable assignment in the initial state. So, in initial state we have a full description of the set of propositions. If the current backward state is consistent with the initial state description, then one can terminate. So, let us now look at the algorithm for backward search, which is called regression. So, in regression we go from G, the goal state, to I, the initial state. So, this function regress takes the following parameters. Init state is the initial state, current goals are the goals, actions, current goals are the current state of the goals, then we have a set of actions, then we have the current path. Now, in this function, if init state satisfies the current goals, then we have got to a state from G to I. So, we are finished, so we return the path. Otherwise, we choose an action, choose those actions from the set of actions such that some effect, there is at least one effect of this action which satisfies one of the current goals. We choose those actions. We chose those actions such that some effect of action satisfies the current goals and the effects are not inconsistent with the current goals. So, we choose such actions, all such actions. If there is no such action, then we return failure. We say that this goal is unachievable. If some effect of the action A, if some effect of action A contradicts some of the current goals, then also that action leads to an inconsistent state, so it can be not be applied. So, you only consider those actions which achieve some sub goal and whose effect does not contradict the current state. So, now we have to find out what is the state that we get by regressing the action in the state. So, let C G prime be the set of current goals minus effects A plus preconditions A. So, the goal achieves some of the sub goals. Okay. So, this action A has, these are the preconditions and these are the effects. Okay. So, we get the previous state by taking current goals minus what has been achieved as a result of the action A, plus we add the preconditions of A. Now, we get C G prime. If the current goals is a subset of the C G prime, then we return failure, because you see we did not achieve anything. If we get back C G prime something which is equal to or more than the current goal, then it is useless. So, we do not consider such states, we reg search at those points. Otherwise, we again regress. We call regress with initial state, the current goals become C G prime, actions remain the same, and the path, with path we concatenate A. And first time we call regress with the initial state, the goal, the set of actions and the empty path. Is this clear? So, this is the regression algorithm or the backward search algorithm. Notice that we search from the goal and there is, so you have to handle the choosing the correct actions, finding out whether they are consistent, the actions are consistent with the current state. So, you have to look at that carefully and you have to know how to get back the regress state from the current state. Now, that we have talked about progression and regression, let us just go back a little bit and discuss the planning algorithm which is used in the strip system. The strip system basically is a divide and conquer search is done. So, the objective is to create a plan to achieve a conjunction of sub goals, and this is done in this way. We create a plan to achieve the goals in isolation, each goal separately, and then we combine this plan. So, we create a combined plan to achieve all the goals. So, what is done is usually we serialize the goal. First we achieve one goal, then we have the problem of achieving the rest of the goals until all the goals have been achieved. So, in strips we divide the goals and then achieve one goal at a time. Now, how does the strips planner achieve a list of goals? It first chooses one of the goals to achieve. If that goal is not already achieved, then the strips planner chooses an action that makes the goal true. Okay. So, it chooses one goal to achieve, finds an action which makes the goal true, backward search, then it achieves the precondition of the action. So, it finds the new goals that the system must achieve, and then it carries out the action and achieves the rest of the goals. Okay. So, this is the algorithm of the strips planner. Now, let us see what are the characteristics of the algorithm and what are the difficulties that we may face. Now, the problem is that this algorithm is unsound, because suppose the goal is written in terms of suppose the goal G is specified as a conjunction of G1 and G2 and G3. Suppose the agent finds a plan to achieve G1. So, this is the initial state, agent takes some actions and as a result of the actions G1 holds. Now, the agent tries to satisfy this rest of the goals G2 and G3, but while the agent finds a plan to satisfy G2, it may happen that in this state G1 does not hold. So, achieving G2 may undo the effect of achieving G1, right. So, we have to be careful that while achieving the goals in sequence, the previous goals are not undone. So, strips does not take care of it properly, and that is why the strips planning algorithm is unsound. Achieving one sub goal may undo already achieved sub goals. In the example that we did, achieving sub goal G2 may undo the effect of achieving sub goal G1, because the objective of the agent is to go to one single state where both G1 and G2 and G3 hold. Now, how do we fix the strips algorithm? There are two ideas that have been tried to make strips sound. The first idea is to protect sub goals. That is, once a sub goal G1 has been achieved, do not take any action that undoes the effect of G1, right. So, protect. So, first strategy to make strips sound is to protect sub goals which have been achieved. So, once G1 has been achieved, do not allow any action that undoes G1. Unfortunately, sometimes it will not be possible So, if you have gone to a state in G1, it may be the case that you cannot get to a state where G2 will be satisfied unless you undo the effects of G1. So, such situations can arise, okay, that G2 cannot be achieved without undoing G1. Okay. For example, suppose your objective is to make cake and buy balloons, right. Suppose the objective is to make cake and be at the park. Let's just revise the problem. The objective is to make cake and be at the park. Suppose you first try to achieve the goal of being at the park, and then you want to achieve the goal of making cake. Now, in order to make cake, you have to be at home. If you are at home, you cannot be at the park. So, you cannot achieve the goal make cake without undoing the effect of being at the park. Okay. So, this condition makes the strips algorithm incomplete. The second strategy to deal with strips is to re-achieve sub goals that have been undone. So, if you first achieve G1 and then try to achieve G2 and G3, but while trying to achieve G2, if G1 is undone, then your objective would be after G2 is completed, re-achieve G1. Now, if you re-achieve sub goals, you might end up in finding longer plans. Now, before we move on to the next topic, mainly partial order planning, we will like to do a brief review of some of the characteristics of planning problems that we discussed in the earlier class. So, please recollect that we talked about the frame problem. In the frame problem, we wanted to specify what does not change. So, when the agent carries out some action, then certain effects, this action, certain there are preconditions and effects of the action, but the rest of the world does not change. Then we talked about the qualification problem. In qualification problem, we said it is hard to specify all possible preconditions. So, we tried to qualify that. And thirdly, we looked at the ramification problem, where we said that it is hard to specify all possible effects. And then we looked at situation calculus. In situation calculus, we looked at successor state axioms. We said that frame problem can be handled by using situation calculus such successor state axioms. For every action, let us say drop action, we say that the effect of drop action is broken x, but we also want to say that if the drop action has not been performed, x will not be broken. So, we say broken x in the state resulting from doing action A from state S if the action is dropped and if x is fragile, or there exists B such that B has exploded and x is next to B and x is broken and we cannot repair x. So, we try to specify all actions which results in broken x, and we say that no other condition x will be broken. So, this is a way of incorporating the successor, the frame condition. Okay. Then in the classical planning framework that we are following, we made certain assumptions. We assume that all actions have deterministic effect. We assume that the agent is omniscient and it is the sole agent of change. There are no other agents in the world, and the agent has to achieve certain goals. Now, let us look at a very famous problem, Bloch-Wolf planning problem, and what are the difficulties some algorithms face to solve this problem. basically the problems that strips face in solving this problem. This problem is called the Sussman-Bloxwell problem or called the Sussman anomaly. The initial state is given by the following diagram, where A is on the table, C is on A, C is clear, B is on the table, B is clear. So, this is the initial state, and the goal state we want A to be on top of B, B to be on top of C. Okay. So, this is the initial state and this is the goal state. Now, let us see how we can achieve. So, the goal is on AB and on BC, right. Now, suppose you take the first of these goals, on not first, the second of these goals, that is you want to first achieve on BC. Now, how can you achieve on BC? You can pick up B and stack B on top of C. So, if you put B on top of C, you can achieve on BC. Okay. Now, after you have achieved on BC, if you are using the strips formalism, you would like to achieve the other goal on AB. Now, after you have achieved on BC, you get a situation like this, B, C, A. Now, if you want to achieve on AB, you cannot do it without undoing the effect of the previous goal. So, this is a very famous problem for which the strips algorithm would run into difficulty. Now, let us look at the Bloxwell search space. This is the initial state of the Sussman anomaly problem. This is the state where C is on top of A and B is there on the table and A is there on the table, and this is the goal state that we wish to achieve, right. So, if we are using forward search, then what would happen? The agent would get here, here, and then from here he can go here, here he can go all these places, etc. So, a forward search one can achieve the goal condition, but if you want to serialize the sub goals in particular way, it might be difficult to achieve this goal. But we can do, if once we have the state space, because it's a very small state space, we can do forward search or backward search. So, let us look at an example of the progression algorithm applied to this problem. Okay. Now, from the initial state, the agent has recourse to two possible actions. The agent can move C from the top of A to B and go to this state, or the agent can move C to the table. Agent has a third action of moving B to the top of C. So, these are the three possibilities that the agent can get to from the current state. Now, suppose the agent chooses this action, then the agent will go to this state. Now, at this state also the agent has how many actions? 1, 2, 3, 4, 5, 6 possible actions from this state. He can move B to top of C, he can move B to top of A, he can move C to top of B, and so on. So, there are 6 possible actions that the agent can perform. Suppose the agent takes the action moving B to the top of C. Again from this state the agent has 2 possible actions, only 2 possible actions, this and this. If the agent takes the particular action, put A on top of B, then the agent reaches the goal state. So, from the initial state, by taking the actions move C from A to table, then move B from table to C, and then move A from table to B, the agent can reach a state which in which the goal is satisfied, and this is a case of success for the agent. And these choices, however, are non-deterministic choices of the agent, and in the actual practice, if the agent will have to do a lot of search. So, this is a particular problem where the state space is not very large. So, this sort of problem can be executed by the agent, but for large problems such search can turn out to be very expensive. Now, let us just briefly look at the regression algorithm that we discussed earlier and see what happens when on the same state space we use regression. We start from the goal and then we apply actions in the backward direction. Again, there is a particular sequence of action: move A from table to B, then move B from table to C, and then move C from table to A. So, these actions bring us back to the initial state. But again, these are non-deterministic choices. If the agent takes these choices, the agent can get the initial state, but finding these will involve a lot of searching. The challenge in finding a good planning algorithm is to make the search space smaller. The reason why STRIPS tries to serialize the goal and achieve one goal at a time is in order to make it easier to achieve the goal and cut down on the search space. So, before we proceed further, let us look at the comparison between progression and regression. Both the algorithms for progression and regression are sound, that is, the resulting plan is valid. They are complete. If the valid plan exists, they find one. But in these algorithms, you need to do a non-deterministic choice, and therefore, you have to use search. If you are using search, you can do different types of search that you have studied in this class: depth first search or breadth first search or iterative deepening search, A star, idea star, etc. But as you know, the complexity of search is exponential in the worst case. So, in the worst case, the time taken for search is OP to the power n, where B is the branching factor. In regression, usually the branching factor B is small, and in progression we need a larger branching factor. So, in progression it is imperative to compute a good heuristics in order to do progression search. Now, we will introduce you briefly to a different type of algorithm for finding plans. Instead of looking at state space search that we have been looking at so far, we will be looking at search in the space of plans or in the space of partial plans. So, before we get into that, let me explain what a partial plan means. Suppose this example is from Russell and Norvik's book Artificial Intelligence: A Modern Approach. The objective is to put on your socks and shoes every morning before you go out. You put on your socks and shoes. Now, you can put on your socks and shoes in many different orders, but you must put your right sock on before you can put your right shoe on, and you must put your left socks on before you put your left shoe on. Now, a plan to achieve right shoe on and right sock on and left shoe on and left sock on. To achieve all this, there are many ways in which you can achieve all this. So, there are 6 different ways of achieving this plan. These are called 6 different linearizations of the plan. You could either first put right sock, then left sock, then right shoe, then left shoe, or right sock, right shoe, left sock, left shoe, or there are 6 different choices, as you can see in this diagram. Or we can represent these choices by the partial order plan. This partial order plan says that you must put your left shoe after your left sock and right shoe after your right sock, but the order between them may vary. So, this is the start state, this is the finish state, and these 4 actions have to be performed in any order so long as they satisfy this constraint, that left shoe is after left sock, right shoe is after right sock. Okay. So, this is an example of a partial order plan. This is a least commitment plan or partial order plan, which only expresses the constraints on the ordering of the different action. So, in partial order planning, the idea is that we have a search space of partial plans when we search in that space in order to find a partial plan to achieve the current goal. Now, when we talk about partial plans, we can immediately handle the problems that strips faced with serial solving of sub goals. We can elegantly solve that problem, as we will see. So, in partial order planning, which we call POP, the nodes are partial plans and the arcs or transitions are refinements to the plans, and the solution is a plan, not a path. Solution is a partial plan. And as I mentioned, in partial plan, we follow a principle of least commitment. That is, we do not commit to a particular order of the actions unless it is required. Now, let us see how we represent the partial plan in the POP framework. A plan is represented by a 3-tuple A, O and L, where A is the set of actions in the plan, O is the set of temporal orderings between the actions, A less than B means A must be executed before B can be executed, and L is a set of causal links linking actions via a literal. We will see some examples. This is the notation. This is an example of a causal link AP to AC Q. So, which means that the action AC has a precondition Q, and this precondition is achieved by the action AP. So, the action AP achieves a condition Q which is required for the action AC to be executed. So, these are called causal links. So, we have a set of nodes which correspond to partial plans. We have a set of temporal links and a set of causal links. Temporal link simply says that if we have two actions, let us say A1 and A3, and we say that this is a temporal link, means A1 must occur before A3. Causal links AP to AC means that AP achieves some condition Q which is required as a precondition for AC. For example, from the blocks world domain, let us take the following example. The action move C from D to B. Suppose this is D, this is C. We want to move C from D to B, and it requires that B is clear. Moving C from D to B requires that B is clear, and B is cleared is achieved by the action move A from B to table. So, this action achieves clear B, and cleared B is required for this action. So, we will have a causal link from the action move A from B to table to move C from D to B. Now, suppose we have a causal link. Now, if we have a causal link from AP to AC, we cannot insert an action, another action, a third action between these two actions if that action threatens this causal link. Now, which are the actions that can threaten this causal link? A step AT. So, if we have a causal link from AP to AC on Q, so AP achieves Q, AC requires Q. Now, if I put in, so suppose this is a temporal link. So, if I put in an action AT between AP and AC, AT is a temporal link such that AT has not Q as its effect. So, if AT has not Q has its effect, what will happen? If so, AP achieves Q, AT achieves not Q. So, if AT achieves not Q, AC cannot be executed immediately after AT, because this Q which AC requires is gone. So, a step AT can threaten the causal link from AP to AC on Q if AT has not Q as an effect, and in that case AT cannot come between AP and AC. Okay. So, for example, let us look back at the example from the last slide. Move A from so we have move A from B to table achieves clear B, and then we can execute move C from D to B. Now, can you tell me an action that threatens this causal link? Can you? So, suppose we have between these two actions, suppose we have suppose between these two actions we splice in another action which is move move X to B. If you have move X to B, now what happens? B is no longer clear as a result of this action. So, not clear B. So, if B is not clear, this action cannot be executed. Okay. So, if we have two causal links and this action achieves the move A from B to table action achieves clear B, which is required for move C from D to B action, no other action should come in the middle that undoes the effect of this undoes this action. Okay. Now, what is the initial plan? So, we will search in the plan space that we said. Now, what would be an initial plan? So, we will introduce two special initial plans. So, initially we have two special actions, one we call A0 and one we call A infinity. We will put these two special actions. Now, what is A0? Excuse me. Now, A0 is an action, special action which has no precondition, and the effects of A0 is the initial state, is the description of the initial state. So, it has null precondition and its effect is the initial state. We also introduce a action A infinity whose preconditions are the goals and it has no effect. So, A0 must be the first step in the plan and A infinity must be the last step in the plan. So, this is what we constrain any partial plan to have A0 as the initial state, initial action, and A infinity as the final action. Now, so in the next class, today we do not have much time. So, in the next class we will cover the partial order planning algorithm in greater detail, but the basic idea in the partial order planning algorithm is that we start with an initial empty plan which has only the initial action and the last action and no other commitment. Then we try to insert other actions so that goals are achieved, right. And where do we pick the goals from? We try to find out a sub goal which has not yet been achieved, and we try to find an action which satisfies some of the sub goal, and we continue until we get a correct plan. So, we will discuss in detail the partial order planning algorithm in the next class and then show how it works. So, before I end, I will like you to think of answer these two questions. I will like you to come up with some examples of planning problems for which forward planning is an appropriate choice. Planning problems for which progression can be used. second question, I will like you to consider some examples, think of some example planning problems for which backward search or regression is the right choice. With that, I end today's class. Thank you.